Okay. Good morning.
Morning.
And we good now? Yep. Okay. And great to be back here at Oshkosh again with all my friends. I'm Barnaby Wayne fan, and the subject for today is, as you can see here, how to really design an airplane. And what I'm hoping to do today is show you how to start from essentially a set of requirements and get to something like a meaningful design. And I've been in the airplane design world for a long time, both models and professionally. As of today, I can count 30 different airframe types that I have worked on as an engineer or designed myself that have actually made it into the air. Yeah, and you know, for those young people out there who are hearing things like you may only work on one or two airplanes in a career, there's a lot happening. Because if you think about it, I've been doing this now for 46 years roughly. So 30 first flights in 46 years averages about one every 18 months. And I'm not done. So there's a lot of cool stuff left to do. And hopefully today I can teach you a little bit about how to get started doing some of that cool stuff. So what's a designer's real job? You know, and this is as opposed to someone who does art, although there is a lot of art in design. The real thing with a designer, as an airplane designer, is you have to produce a specification for a machine that'll work in the real world. And the other thing that takes a lot of getting used to for engineers, I think, is that the airplane is fundamentally a tool to do something for an end user. You know, and we tend to fall in love with the machine, how cool the machine is, but fundamentally it has to do what the person who's paying you to build it needs done. And that's really at the core of it. And what you think is cool or elegant really doesn't matter, except as a tool to how to produce a good design for that customer. So when we start out, what are we thinking about? First order, functionality. It's got to work as a machine. The reason I have the words "the machine must fly" there is if you go back and read the very first official government request for proposal ever for a heavier-than-air aircraft, which the Army Signal Corps issued to the Wright brothers, the very first specification was the machine must fly. It's still true. And believe it or not, every now and again, even in relatively recent history, there have been aircraft that have been completed and tested and refused to leave the ground. All right. We'll ignore that one missing chart. Here's the really important thing. The first job of a designer is to get real. And you know, a doodle or a sketch or a CGI image or an AI image is not a design. And you know, if you have been in this whole wonderful world of experimental aviation for so long as I have, you keep hearing things like, I have a design for an airplane that will X, Y, Z, or I'm designing an airplane, and what the person really has is technical equivalent of a napkin sketch. I mean, I just recently on a message board that I frequent saw something that said, I am designing and I'm not going to put specifications because I don't want to embarrass the individual, but an incredibly capable airplane that'll do all this cool stuff, and I need help on shape and materials. Okay, so this person has a dream, but not a design. Because it's remarkably easy to do something like this. I mean, look at this. Isn't this wonderful?
That's amazing.
Now, it has evolved since 2 years ago when I started this talk. It's now hybrid electric propulsion. But the point here is, I mean, that's amazing. And, you know, within my limited CGI skills, it looks real. It's not. But it is pretty cool. I really, frankly, want to build an RC model of it just to prove that it can be done. So yeah, your job is to get real, because the design is a complete specification for something you could build and operate in the real world. And the thing to realize is that the big wins and losses happen at the basic vehicle architecture stage of the design. And this is, by the way, and I'll talk about it a little bit more in a moment, why I always start with pencil sketches. Work out the basics of the concept. Because it is possible to ruin a good concept with bad detail design, but no amount of good detail design will save a bad concept. So, when you make those early decisions, and it's an interesting dilemma a designer faces, because early on in the design process, you have very little information. But it is the point at which your decisions have the biggest leverage, and it gets more and more costly to change them as time goes on. So learning how to make good early design decisions is really important. And that's really what designing is making a set of decisions. So, every design starts as a sketch. Now, some people do it digitally. I'm old school. I do it pencil. And, every one of these was something that I was thinking of at least semi-seriously. Even the bat plane. Now, if you look here, you can see on some of these, I'm actually starting to do some preliminary calculations like wing area and where the spars would go and things like that. And if you look at my notebooks, what you will see very often is I'm drawing the same thing over and over and over again, and it looks like I'm repeating myself. But if you look carefully, each successive sketch has a little bit of a change as I'm figuring it out. One of the things I love about a pencil is I can erase things and change them without rebuilding like a whole CAD model or something like that. Now, the CAD model becomes an incredibly powerful tool after you've got the basic architecture figured out. But this is the way I always start. And the hope is that at some point, one of those sketches will turn into a real airplane. And this is a case of exactly that. This is an ultralight that I built about 15 years ago. And this is the actual first sketch of it. And you can see I had it pretty well figured out. Not perfectly. Like, for example, here on the aileron, it's a little bit different shape here. This one only has two ribs, not three. Little details like that. But I had the architecture done before I went to the computer and started doing the CAD model. And then what you end up in is what is essentially an iterative loop. This is kind of the whole design process. You start with a customer who wants an airplane. They give you a specification. What do we need it to do? Then you come up with what we call the concept of operations, which really has to do with where do we operate out of, what kind of fuel do we burn, what things like that. And then you go through usually a bunch of configurations, and then you iterate those configurations in this loop, deciding, does it finally do what I need it to do or not? And then at some point you go to further refinement, and then the customer either says your deadline is reached or your engineers are actually satisfied. Both of these can happen, and you deliver a product to the customer. And, if fate is kind, then you take that design and you actually get to build the airplane. So, what we're talking about here is conceptual design, which starts with requirements definition, then we define a mission profile and concepts, then we lay out an airplane, and then we iterate and refine that baseline design. And the importance of a baseline design is really, really critical in that design process. And what the baseline is the best you have at the moment. Ideally, it is the solution you have now that will at least meet the minimum requirements. And then the objective of each iteration is to knock that baseline off the pedestal with something better until you achieve whatever your criterion for good enough is and ship it. So essentially, design is, as I said, making a series of decisions, answering a series of questions. So the first question is who? Who's my customer? Who's going to buy and operate this airplane? You know, and that can range, right? I mean, in the EAA world, sometimes the answer is me. That makes it both very easy and very hard for the designer, right? Sometimes it's, for example, the US government. I'm involved right now in a competition for a future, and professionally for a future force structure airplane where, you know, the government has given a specification for what they want this next airplane to do. And we're trying to design to that. You know, if you're designing an airliner, your customers are the airlines, and they may not give you a request for proposal, but you know what they care about. Reliability and fuel burn. Next question. What do they want it to do? What is the mission? We're designing a tool for a user. What does this tool have to do? In the EAA world, a lot of times it's amuse its owner and don't kill them. That's it, right? In the military world, it's a much, much more stressing thing. And then you have special mission or single mission airplanes like airliners. Transport people safely from here to there with great reliability at minimum cost to the operator. Each one of those things gives you a very different shaped machine. Also, very important, where do I have to operate out of? How much runway do I have? What kind of density altitude? What kind of fuel is available? You know, an airplane to operate out of 1,000 feet of unimproved strip in the bush country is a very different airplane than one that can take off out of O'Hare and LA International. So those are the kinds of decisions you're making. Now, there are some universal requirements. First of all, it's got to be airworthy. It's got to fly, and it's got to fly safely. Now, the detailed airworthiness requirements may change. The rules you're designing to may change. But that fundamental fact that it's got to be an airworthy machine doesn't matter what the rest of the mission is. Structural integrity. Obviously, airplanes falling apart in flight is not good. We want to avoid that. It has to be reasonably operable. You have to be able to keep it in operating condition, maintain it. And it doesn't matter where you are in the spectrum, from billion-dollar military programs to building an ultralight, the customer has to be able to afford to buy it and operate it. So those are universal. Some of them are absolutes, some of them are a spectrum. So once we've established that, now let's starting to take a look at the design mission. So what does this tool I'm creating have to do? How much? How much does it have to carry? What's the payload? What's the range? How far? How fast do I have to go? Do I care? Is there an altitude? Is there an endurance requirement? Once again, depends on the mission, right? Nobody really cares about the endurance of an airliner, but when I'm designing a sensor platform like Global Hawk, the customer cares a lot about how long I can hang out and look, right? Is there an altitude requirement? And what else? Because, you know, these are the basics. Who knows what other missions they may have? So then we start with what's a basic mission profile. And this is the simplest sort of a mission profile, which is, you know, taxi, start up, climb to altitude, cruise out, do something. Sometimes there's a segment in the middle there. If it's a military airplane, it's either, you know, combat, drop the payload, or if it's a sensor platform, hang out. Cruise segment 2, descend and land somewhere. Sometimes it's back at the original base. Sometimes if it's just a cross-country mission, it's at your destination. And, you know, you have to look at other things. Like, for example, the standard FAA IFR mission has a 20-minute hold and a divert to an alternate airport built in. You know, so there'll be things like that. And like some military missions have a low altitude ingress part of the mission. But basically, you want to start out with this because this is what the machine has to do. It has to be able to execute this trajectory. And all of your performance calculations and sizing are based from that. And as you're making those decisions, the mission defines your decisions. Mission first, then configuration, a very common mistake. you know, if you've been around as long as I have, you've seen multiple FAD configurations. Sometimes they're actually good for one or another mission. Sometimes they're not a bad idea, but they're not the universal solution for everything. And if you fall in love with a configuration first and then try to force it into a mission, you're liable to end up with a badly compromised airplane. You know, there are some missions for which something really cool, exotic, and innovative is the right way to go. And you have to, nothing but to look at the STOL world to realize there's some places where a good old-fashioned high-wing, strut-braced, fabric-covered airplane is the right way to go. So, mission first, then configuration. Don't fall in love with a concept too early. I mean, and we're all guilty of it if you're a designer. There's just these things that you think are too cool. You have to make it work. And beware of requirements creep. This is a big deal because it's just a little more, right? I start out with my 150. Okay, well, it'd be nice if it was a little faster. I'll put a little bit more power. Gee, it's burning more fuel, right? Make the wing a little bigger. Oh, and another back seat would be nice. And maybe we retract the gear, and the next thing you know, you've got a 210, and you've tripled the price. And, you know, this is a big deal in the military world because the customer always comes back and says, yeah, that's cool. We've got this new missile that's 6 inches longer. Can you fit that in too? Well, yeah, but it'll cost you. So be careful about those requirements creep. Okay, so, I mean, I've said this a little bit, but once again, in the requirements world, you have to break it down. First of all, there are constraints. Constraints are you can't break this box. So, for example, if I have to take off in 1,500 feet because there's a wall at the end of the runway, that's it. I can't go further than that. Very often you'll get a request with what they call a threshold. That's a minimum acceptable performance. And what the customer's telling you is if it won't at least do this, not interested. Then there are goals, which is the maximum desired performance. And those are important to look at too, because what the customer is telling you is you don't get credit for more than that. And that in turn means that if you try to give them more than that, you're giving them something more expensive. You know, I advise at several universities, and every year in senior design, there's one team that will proudly tell us how much more performance they give than the request for proposal. And it's kind of sad when I always tell them, well, guys, what you have just shown me is your airplane is more expensive than your competitors. So take a look at what that max goal performance is also. Now, sometimes more is better. If you're racing, faster is always good, right? And I have never met a sailplane pilot yet who will tell me less L over D is a good thing. But you know, you're going to have to make compromises along the way. It comes with the territory. Now, there's a couple of great examples from history where people did a brilliant job of the mission drives it. One of them is the Spirit of St. Louis. And if you want to really read a beautiful description of a good interaction between a customer and a designer, read Charles Lindbergh's book called The Spirit of St. Louis, because there's a big segment in there about him working with Donald Hall, who was the designer, as they created this airplane. Now, the interesting thing is, the mission was in the name of the airplane. Ryan NYP, Ryan New York to Paris. That was the only mission of that airplane. And you take a look at the design compromises they made along the way, because they also had to build it in some insanely short period of time. I think it was 90 days, to try to beat the other competitors. So he's talking to Donald Hall. So one of the things is, okay, you've got to carry this insane amount of fuel. Well, to make it balanced, you want that fuel near the CG. Well, where's the right place to put the fuel? In front of the cockpit. Also, you know, in a crash, Lindbergh would much rather be behind 450 gallons of avgas than in front of it. And, you know, Donald Hall said, well, okay, but you know, you're not going to be able to see forward very, very well. And his reaction is, I can take off and land looking out the side, and there ain't going to be any air traffic to worry about over the Atlantic anyway. Right? And then Hall asked him, where do you want the second seat in this airplane? Well, Lindbergh said, I'm going by myself. I'm single pilot. And Hall said, yeah, but the airplane will have no further use after you make the flight if you don't have a second seat. And Lindbergh said, I don't care. It just has to get me to Paris. Exactly right. He didn't carry the weight. And what's interesting is you read about how Lindbergh was thinking. He's thinking about every ounce in terms of how much more gas he can carry. And the final compromise, and this is an interesting one because it was accidental, they used standard Ryan M2 mailplane tail surfaces to save time, to not tool additional ones. And Hall was worried about it. He said, well, your stability is going to be kind of not so great. And it wasn't, which ended up saving Lindbergh's life because the airplane was so unstable that when he started to fall asleep over the Atlantic, the airplane diverged. It side slipped enough to blow cold air in through the window and wake him up. And he said, but with the small tail surfaces, we'll save a few ounces of gas also. But brilliant piece of ruthlessly keeping the airplane matching the mission. And if you read the history of that Ortrig Prize, the other competitors all were flying bigger multi-engine airplane, multi-crew, and not one of them succeeded. Several of them crashed on takeoff, several of them. So, beautiful example. And then there's another airplane, less famous, but super important in my life. This is actually in the EAA Museum. This is Ed Lesher's Teal. And, subject for another day, but this airplane and that man changed my life. He was my mentor. But Ed set out to set records in the 500 kilogram takeoff gross weight class. And he designed this airplane to do it. Once again, brilliantly clean design. It's got a retractable landing gear. It takes 11 separate operations to raise the gear because all of it was little thin pull cables to save the weight of interlinks. Not only that, when he started building the airplane, he weighed about 210 pounds. He dieted down to 170 before he took off. Okay, saved like 40 pounds. 40 pounds is what, 8 gallons of avgas? Airplane got 40 miles to the gallon. He added 320 miles to the range of the airplane by changing his diet. Ruthlessly mission focused, and he, by the way, set distance records. Brilliant design, beautiful airplane. It's quite rightly in the EAA Museum. But another story is how important it is to understand customer requirements. If you go back about 30 years or so, Airbus was working on the A380, and Boeing was working on a stretch 747 that they called at the time the 747-800, which eventually they later built, by the way, as a 747-8. But at the time, they canceled the stretch 74, and Airbus went on with the A380. And there was great lamentation in the trade publications of, oh my God, the Europeans have stolen the march on us. They're going to have the biggest airline in the world. We've been left behind. And then Boeing said, well, we're going to do this instead. And by the way, this was not a cartoon. They meant it. I'll leave you all the quotes here. But their basic idea was this. Technology has improved so much. There's better engine technology. We've learned a lot aerodynamically from our SST programs. There's better materials technology. We can build an airliner now that will cruise just under the speed of sound. Because remember, it's still, at that time at least, still illegal to fly civilian over Mach 1 over the continental United States. And the idea was that with all this technology, I'll still burn less fuel than a 7.6 per fuel mile. I'll go this much faster. I'll get more productivity. I'll fly higher. I'll be out of the traffic. Isn't this cool? And they went out and they were aggressively marketing this airplane. But you see, every good engineer tries to anticipate the questions that are going to get asked. And one of the questions they knew were going to get asked is, okay, what if you took all of this cool technology and put it in an airplane that's less weird? A conventional airplane. And so they designed an airplane strictly to be a straw man in their proposals to show how good the Sonic Cruiser was. And they went out and started making their presentations. And the airlines all said, well, you know, your spaceship over there is kind of cool and going a little faster is okay, but I can't sell my customers that 10% speed, but you're giving me another 10% reduction above that in fuel burn, that we will buy. And so Boeing was smart enough to say, okay, cool, we'll build that. And so it went from the straw man to show that the Sonic Cruiser was good to the 7E7 to the 7X7 to the 787, which is still in production to this day. And by the way, it also, because of its fuel economy, broke the hub and spoke model, which broke the business model for the A380. You know, and Airbus ended up losing a ton of money on the A380, and Boeing may actually make money on the 787 at some point in its life. Okay, so as we're designing an airplane, we start out with initial concepts, and very often there's more than one viable configuration for the mission. So we're going to explore several approaches, and it became anywhere from quite conventional to seriously innovative. But here's the thing. Anytime you deviate from conventional practice, you're adding risk and you're potentially adding cost, so that innovation, that unusual configuration, has to have a meaningful advantage in the performance of the mission to be worth doing. This is why conventional high-wing, strut brace, wing body, tail airplanes are still around. So start with multiple concepts. Once again, these are from actually a design study I did for a manufacturer wanted a new single-seat ultralight sport airplane. And you know, you go from very conventional. These two, for example, were optimized for simplicity of structure. I called that one a MIGlet. It was supposed to look like a MiG-21. It didn't balance. And then various exotic configurations. And you down select. And they actually picked one of these. And we got as far as a quarter-scale RC model, which flew beautifully. And then, unfortunately, that company decided to go a different route with something even more boringly conventional than anything I could design for them, because they didn't ask me to design them a conventional airplane. And so this never got beyond the model stage. But that gives you an idea of how you go through the initial concepts to down select to picking something. You know, as we talk about innovation, you know, the trade between risk and potential is a fundamental discriminator between concepts. There's some risk in any new design, right? You have to make a whole series of right decisions. The more I deviate from standard practice, the more I have to learn in order to make it work right. And so there has to be a payoff to it. And you can kind of put these in buckets, because all three approaches can work, right? You can go radical. I mean, canards aren't radical to us now, but when Bert first brought out the Very Easy, you bet it was, right? You can stay very conventional, as Vans does. And, you know, one of the things Dick Van Grunsven said to me some years ago when we were just sitting chatting at Oshkosh was, sometimes the key to success is doing ordinary things extraordinarily well. And if you had to describe how Van's aircraft works, that's it. And obviously it works. It works very well. They make great airplanes. Or you can take some technologies to get some more performance without taking the risk of going full radical. So you take a look at something like the Lancer Legacy. Laminar flow airfoil composite structure. Real advantages to that. It's faster. Maybe the flying qualities aren't quite as good, so there's a little bit of a risk balance there. But you can take any one of these three approaches. Something I tell all of my students: conventional practice is not conventional because the old guys are stupid or lazy. It's conventional because it works. And the thing to realize about, although it's an interesting loop, is everything that is now conventional practice was somebody's radical idea at one time. Right? You go back to the Wright Flyer, it was a canard fabric-covered pusher. with no enclosed cockpit. We got all the way from that to supersonic jets with everybody's radical ideas, the ones that got adopted and became conventional. Very often, the way a radical design gets adopted is you can't do the mission that the customer needs to do with a conventional design. And sometimes even that will end up with the rehabilitation of a concept that had other advantages, but was too risky to try. And a beautiful example of that is flying wings. You know, Jack Northrop had the benefits of the flying wing figured out in 1947. If you want to read an absolutely brilliant technical paper, find his 1947 Wilbur Wright lecture about all-wing airplanes. And everything he said about range payload performance was 100% correct. But controllability issues, all kinds of worries about unconventionality. Okay, roll things forward to the late 1970s and the height of the Cold War. The US Air Force needs a new bomber, which has to penetrate the Soviet air defense net, which the B-52 cannot do. Well, if they just needed a more efficient bomb truck, they would have had Boeing build something that looked like a B-52 with a 787 wing. But those pesky radars can see it from 200 miles away. So guess what? The only way to do it is to revive the radical flying wing concept. Now that the B-2 has been operational for so long and proven the flying wing concept, and by the way, quietly proving the range payload performance also, you now have companies like JetZero, for example, talking about blended wing body airliners, and a tailless airplane or a flying wing is considered a very ordinary configuration to choose. But it had to have the mission that no one else could do with any other configuration to make it over that threshold. And this is something, I put this in the talk after the Titan submarine disaster, because the late Stockton Rush kept talking about how innovative his submarine was right up to the moment it killed him. But we tend, and we do this in teaching and we do this a lot in industry, to use the word innovative with a capital I as a synonym for good or advanced or better. If you take the rigorous definition of innovative, all it means is it's different. Different is not always good. Sometimes it is. But if you're going to be innovative, you need to make sure that that change, that innovation, that new thing makes the machine better in some useful way. That's what makes it worth taking the risk of deviating from conventional practice. Because there's lots of ways it can go wrong. First of all, your innovation may not improve the airplane. You may take the risk and not be any better. Another one, and this is very common in student projects, is what I call hobby shop syndrome. You put all of the innovations in one airplane. The problem with that is if I put 9 or 10, let's say 10 new high-risk things in one airframe, and 9 of them work and 1 of them doesn't, the whole project fails. So if I'm doing a radical configuration, I don't want a new magic engine, unconventional flight controls, and different materials too. 1 or 2 innovations at a time. And you know, in my own personal projects where I am playing with radical configurations, everything else is as boringly conventional practice as you can get. You know, riveted aluminum, not carbon fiber, conventional engine, things like that. We have this idea of technical fads. People fall in love with configurations. For a while, canards were everything. Then it was blended wing bodies. You know, that's why I did a forward swept triplane for my original, CGI, because that's my throwaway. Well, what about a forward swept triplane? You know, and another one that is a really important and catches people out is non-standard flight controls. Pilots are trained kinesthetically to operate the stick and throttle a certain way. People have tried things like overhead sticks or, let's fly like a bird controls, and what happens is the pilot reverts to muscle memory when the task load gets high and bad things happen. This is, by the way, one of the reasons why it's very difficult for someone who learns on a weight shift trike to transition to a conventional airplane or vice versa, because the sense of the controls is reversed. And they both work if you train them properly, but switching back and forth is hard. Okay, so we've got our concepts. Now we're going to get into sizing and layout. Now we're going to get into the guts of it. So, once again, 3 basic questions. Size, bones, and balance. This is the mantra I teach my students. How big is it? How much engine does it need? How big is the wing? Fuselage size, all that. Basic sizing. Bones, load paths. Draw the structure in early. The number of preliminary sketches I have seen where the spar ends at the side of the fuselage and would have to go through the pilot's kidneys. Holes do not carry load. And so you want to have the initial structural layout, at least the big bones, right at the beginning. Because very often you're designing around the things that have to go into the airplane. And then does it balance? Because you can have a design that's otherwise wonderful. If the CG's in the wrong place and you can't make it balance, it doesn't fly. So size, bones, and balance. So if we get into sizing, you start out with the fact that the weight of the payload, because that's specified by the customer, and the crew are pretty constant. There's not much I can do about that, right? That kind of sets the weight, if it's a conventional wing body tail airplane, that sets the weight of the fuselage pretty much, because it's got to surround all that and carry that. Okay, what have I got left to play with? Fuel, wing size, engine. The other thing you have to watch out for is there's this wicked cycle, which we call the wrap rate in weights. Every pound of arbitrary weight you add to an airplane increases the takeoff gross weight somewhere between 3 and 5 pounds. Because if you think about it, if I've got my airplane designed to carry your payload and you come with a 1 pound gold brick and say, oh, I want to take my precious brick with me too. I say, okay, I'll put the brick in. Gee, that means I need a little more fuel to make range, right? Okay, I'll add the fuel. Oh, but I have to maintain stall speed, right? That makes the wing a little bigger, which is a little heavier, which means I need even more fuel, which means maybe I need a little more engine. And by the time you get done with that iteration, you've gained between 3 and 5 pounds. So this is, weight is one of those cycles that can be either a virtuous cycle as you take weight out or a really wicked cycle as you add weight. So if we're going to do an initial weight estimate, go back and look at historical data, because if you look at historical data, what you discover is the fraction, the percentage of takeoff gross weight that certain things are, is relatively constant, particularly payload fraction, for airplanes of similar class and similar use. So here's just an interesting thought experiment to show how this works, because Cessna obliged us by doing 2 airplanes for the same mission with basically the same level of technology in them. They're both aluminum airplanes with roughly the same configuration, powered by a flat 4 air-cooled engine, right? So if I look at the weight fractions on the Cessna 150, you can see that it's about 63% empty weight. The fuel is about 10%, and the payload, meaning the people and baggage, is about 28% of the takeoff gross weight. It's not remarkably good, but 150 is a great little airplane for what it does. I have one, I love it. Now look, 50 years later at the 162. And lo and behold, remarkably close to the same weight fractions. Very close. They shuffle things around a little bit. So if I were the preliminary designer setting out to design this new high-wing strut-braced metal airplane, starting from a 150, and I were to predict the weight of my new one based on just the fractions of the 150, the blues are actuals and the reds, oranges is what you would have predicted cold from the weight fraction model. So you can see that gets you close enough to do your initial sizing, and then you can do your iterations to refine from there. And it's really important to get this right, because a lot of times people will arbitrarily pick a weight. Now, before Mosaic and Light Sports, you had no choice. You were designing to 13, 20 pounds, and everything you were doing was trying to get the empty weight down to get the payload fraction up. Because this drives everything. You know, and I pretty much said all this, but because fuel and people don't scale, so you're stuck with that, and then you're doing the rest of it. Engine installations can bite you big time. You know, if you're just slapping the engine on the front of a tractor fuselage, not bad. If you're doing a stealthy jet where the air has to go through tunnels through the engines in and out, the weight of all of that ductwork turns out to be dramatic, and it can actually affect the optimum size of the engine. You know, the engine that you would pick in isolation as the optimum isn't the optimum when it's integrated because of what all of the installation issues are. Okay, with wings, wing loading is the primary driver, primary sizing parameter. And that gets sized by a bunch of things. Cruise tends to drive you toward higher wing loading. Takeoff and landing and stall speed tend to drive you to lower wing loading. And sometimes regulatory. Sometimes maneuver requirements, but not usually unless you're doing a fighter or an aerobatic airplane. For example, if you're certifying under either Mosaic or Part 23, there's a stall speed limit at a specified configuration. That'll set your wing size, almost for sure. You know, Part 23 is 61 knots with the flaps down at gross. Mosaic, depending on, you know, has a few stall speeds. Wing size scales linearly with gross weight because you're basically designing a constant wing loading. And the wing weight is a strong function of the aspect ratio of the wing. So there you're trading lift to drag ratio against weight. Low aspect ratio is lighter, but lower L over D. Stall speed drives takeoff distance because if you just look at the physics of acceleration, at constant acceleration, the distance to get to a given speed goes as v squared. That's one of the reasons, by the way, why ultralights take off so short, because they lift off at 30 miles an hour. So if you think about it, the difference between that and the 60 miles an hour that I rotate in my 150 is a factor of, I've doubled the takeoff distance. That means I've quadrupled the takeoff roll. Okay, so, I mean, this pretty much just summarizes what I've just said. But there's another big one in terms of stall speed, and that's survivability. And this curve is a bunch of SAE crash data, crash survivability data, reformulated in terms of high wing loading, high thrust to weight, right there. But this is in terms of impact angle with the ground on an unintentional meeting with the ground, and stall speed, or speed at impact. And there's an amazing amount of information in this chart. First thing is that 45 knot stall speed that Light Sport and Mosaic talk about, it's not irrational. If you look at it, what that 45 knot speed is saying, oh yeah, by the way, if you're on this side of the curve, you're dead. If you're above the curve, you're dead. What that says is at 45 knots, unless you fly into a brick wall or impale yourself on a flagpole, you'll probably survive. That 61 knot speed for Part 23 is not irrational either. If you look at it, okay, that's about a 30-degree impact. Well, guess what? At stall, if I keep it a little bit above stall, what it's telling me is if I keep the airplane under control and just glide into the ground, I'll probably live. Here's the one for people who are playing with high wing loading experimentals, because we don't have, in EAB, we don't have that stall speed requirement, right? Out here at about 78 knots, even a flat impact on random terrain will probably kill you. Now, to airplane people, that's a little surprising. 75 knots doesn't seem that fast, but it's over 90 miles an hour. So imagine being placed in a car and randomly dropped in random terrain at 90 miles an hour with no brakes and no steering. That's what that kind of impact is. Now, what I've done here is to say put lines of constant wing loading with approximately the stall speed. So this is why you say, okay, I don't want to get much above 20 to 25 pounds per square foot wing loading in a light airplane for survivability. And that's for that dead stick impact with the ground. So if you're taking off in your very high performance, high wing loading composite airplane, you want a very, very reliable engine because you're going to have to find someplace smooth to land on actual landing gear if you have an issue. So wing size, induced drag is a function of span loading. So you can improve L over D, you can reduce induced drag and improve rate of climb by increasing span or by reducing weight. And if you come on Thursday when I talk about low aspect ratio airplanes, I'll show you how going extreme in the other direction can also work. But once again, it really depends on where you're flying. So cruise, at high altitude, you're dominated by induced drag. You're flying near best L over D, so your drag is about half induced drag. At low altitude, particularly in a wing sized for stall speed, it's almost all parasite drag. You can get away with lower aspect ratio and save the weight without any real meaningful penalty. So the optimum depends. So you look at it, airplanes designed to cruise and loiter at very high altitudes are all very high aspect ratio. When you start getting down to low altitude, high wing loading, lower aspect ratio, and probably higher wing loading. And then, of course, ground handling. One of the problems with the A380 is only a few ramps can fit it. And to show you how important that can be, Boeing was willing to take the technical risk and weight and cost on the 777X to make folding wingtips and certify an airplane with folding wings just to be able to use all of the standard airport infrastructure and not run into the A380 problem. This gets back to the mission. Where do we operate out of? One of the big problems with the A380 is only a few hub airports were willing to build the special taxiways and the special ramps to accommodate the wingspan. Boeing saw that and said, okay, we'll eat the weight and cost on the 777X to fold the wingtips, but it's still worth it to get the extra span for the cruise efficiency because it's a long-range airplane. And hangar size can be a big deal also. One of the reasons most light airplanes have a wingspan of not greater than 36 feet is for many years, the standard T hangar that everybody had at little airports was 38 feet wide. And the cost to go into an executive hangar for your 42-foot span Piper Malibu is 2 or 3x on hangar cost. So make the wing a little shorter, eat the extra fuel burn, save it back on hangar. Operability, right? Engine, same thing. You've got a size for multiple things. A lot of airplanes are sized for takeoff and climb. What's interesting, though, is when you start sizing the engine for cruise, for a fast airplane, it gives you some freedom to do things for takeoff and landing that you wouldn't otherwise do because you've got all that extra thrust to weight. So once again, slower airplanes, it's usually takeoff and climb that size the engine. If I've got a high speed requirement, it tends to be cruise. Sometimes dash or acceleration. On fighters, the engine is sized for hard maneuvering because you're trying to maintain speed pulling somewhere between 4 and 7 Gs. Well, remember, induced drag goes as lift squared. So if I'm pulling 4 Gs, I'm making 16 times as much induced drag as I am in level flight, which is why a fighter even with a thrust to weight greater than 1 can only sustain somewhere between 5 and 6 Gs without losing energy. Problem with that is it's an interesting design problem because I have this design point and the customer says, you got to do it. Now that airplane spends most of its life cruising a lot slower than its top speed subsonically at 1 G, which means my engine is completely missized for the place I'm going to spend most of my time, but I have to hit that 1 point. And once again, you use the thrust to weight from comparable airplanes. You start from historical data. Final thing, in your sizing software, you can scale engines infinitely if you've got a good cycle deck, but the engine manufacturers will not sell you a 0.9 scale engine or a 1.05 scale engine. You have to go to unless they're designing the engine for you specifically, you have to go and say, okay, I need an integer number of scale 1 engines. So now that we've done all that sizing, we can actually start drawing the airplane. We can start out with a relatively crude sketch. Once again, we're getting the architecture right. Size, bones, balance. We've done the size. We know about how big it is. Now it's bones and balance. Does everything fit? Can the pilot see? Can we get stuff in and out? So the sequence is you start by laying out, we used to call this at Northrop, laying out the deck chairs. Fit the big pieces in. The payload, the pilots, the crew. Where do the engines go? Where does the landing gear go and what's the load path for the landing gear? The number of drawings I've seen where the landing gear is just a lollipop sticking down out of the wing and the stick of the lollipop ends at somewhere where there's no structure. You know? You got to figure it out in advance. And then basically, once you've got the core of the airplane, you adjust the flying surfaces to make it all work. Now, my friend Dan Ryan, who designed multiple aerobatic airplanes, was kind enough to let me use his preliminary design sketches. These are the sketches that actually led to the DR-1071 design aerobatic airplane. So you can see some of his early sketches. He's already getting the pilot in. You notice how he's already got the pilot's knees, the spar going under the pilot's knees. He's figured out the load path, you know, about where the truss goes, about where the engine hangs, right? So having done that, you now start figuring out where the flying surfaces go. You know, if you look at this, you can already recognize the final airplane, but you can also see this is not it yet. And then you get eventually to a final general arrangement where you've got everything sized, you know, everything fits, things are sized for the right flying qualities, it balances, and that's when you're ready to go to detail design and eventually hopefully build the airplane. So, you know, we've covered this pretty much, but main structural elements need to be in that initial sketch. Where does the spars go through? Where do the wing loads go? Where does the landing gear load? How does the fuselage carry tail bending loads? The big deal if you're going to have a door. Holes don't carry load. You know, it's really easy to sketch like a high wing airplane and then realize the floor is 3 millimeters thick and the ceiling is 3 millimeters thick and the door makes a nice big hole in that structure. Doesn't work real well. So you need clearances for frames and load-bearing skins. You know, if I shrink wrap around the payload, there's no place for the structure. And I will tell you from experience that structures guys will fight you tooth and nail for an extra inch of outer mold line to put the cap on a bulkhead. On one project, I actually redesigned a wing to make it locally thicker because it wasn't aerodynamically critical. And I went to the structures guy and said, I can give you another 3 inches over the landing gear bay. And he did a double take and looked at me like I had 3 heads and asked me, are you sure you're an aero guy? Because no one's ever offered to make the wing thicker for me, ever. Then, okay, secondary stuff. Where does the gear attach? Where does the tail attach? How do you support the payload? You know, if I'm carrying stuff in the back, you know, in a luggage or cargo, got to have a strong cargo floor, got to have tie downs. How are we doing on time, Kate? Okay. Holes don't carry load. Take them into account. Transparencies in particular can catch you out because they don't look like holes, but they are, because the transparent material doesn't carry load and it's also heavy. So eventually you get to a full structural layout, and this is the actual, off the actual CAD drawings for the DR-107. This is where the structure actually goes. Finally, it's got a balance. And the important thing is that the CG of the airplane can change in flight. So the first thing is it has to be able to balance, be within its acceptable CG range at zero fuel with the worst case loadout, whether that's lightweight pilot or heavyweight pilot, right? So you have to analyze both the forward and aft loading, and it should not be possible to move the CG out of the safe range in flight. And there have been airplanes where this happened. You know, on military airplanes where we drop big masses out of the airplane mid-flight, it's a big issue. But just fuel burn can do it. And there was a problem on some of the early fast class airplanes where they had wing tanks and a cowl tank. And the cowl tank was normally thought of as reserve fuel. But it turned out that on some of them, if you had too heavy people aboard, when you started burning the fuel out of the cowl tank, the CG would go behind the aft limit. Which means that the stuff in that cowl tank isn't really fuel. It's flammable ballast. Now, ideally, we want to minimize the CG travel. So what you want to do, first of all, is have the empty CG of the airplane somewhere inside the allowable range, and then you try to move the variable loads as close as possible to the empty CG. And in the perfect world, all of those changes are within the CG envelope. Because the further out you move those loads from where you want the CG, the more the CG changes with changes in that load. And large CG travel, you can make it viable with a big tail and so forth, but it causes issues. Tail weight, trim drag, various other things like that. So here's how you deal with it. You start out by making a side view of the airplane. Each one of those plimsoll marks is a single mass. And then you can do the calculation of weight of center of gravity from here. I'm not going to go through the math right now. One of the things you'll notice, I have the datum set ahead of the nose. On most actual airplanes, when you're doing the calculations, like from a pilot's operating handbook, it's a physical thing you can measure on the airplane. On the drawing board, we always put the datum ahead of the nose so that if I change the length of the nose, I never get a negative fuselage station in my calculations. So like at Northrop, for example, we always start with the nose at fuselage station 100, the actual nose. And so the datum is 100 inches ahead of where we start. And then as you do the calculation, you end up with what we call a potato plot, which is all the possible. Each one of those dots represents a different loading on a hypothetical airplane. And the idea is this, the x-axis is mean aerodynamic chord. You want those to fall within the limits. Now, once walking around, I actually found a prototype where they marked it all right on the wingtip. Gotta love that. So here's the situation that I talked about with the cowl tank. I take off at the top there at full fuel, max gross weight. I burn the wing tanks down, the CG's moving aft. I burn the cowl tank, and if my aft limit is at 30%, where it was with my original small tail, I'm unstable. And then, you know, if I had less occupant weight, this would all move forward. So the solution at the time was to make the tail bigger. So now the F limit's at 32%, and you're fine. So the limits are set by different things. The forward limit is set by nose, either trimming the airplane to stall at most forward limit or nose wheel liftoff. The aft limit is usually set by stability. On unstable fighters, it's set by the ability to push the nose down from high angle of attack. So we said that already. And you end up with, there's a parameter called tail volume coefficient, which is a non-dimensional way of looking at the size of the tail and taking the tail arm into account. And as you increase the tail volume coefficient, which is either increasing the tail arm or the size of the tail, the forward limit moves forward and the aft limit moves aft. And basically what you want is you can pick a tail size or a tail volume where, in this case, those dotted lines would represent the most forward and most aft physical CGs. And so on this particular one, this is a nicely balanced design. They both end up at about 40%, 0.4 tail volume coefficient is right. And you can tell from this plot also whether you're nose heavy or tail heavy airplane by which of those two limits sizes the airplane. Ideally, in the perfect world, they both hit at the same time. The world is rather rarely perfect, but still. And so, in the end, if you've done all this right, you end up with what we call a closed design, which means it's buildable, it's balanced, it's airworthy, and it meets the performance requirements. There's, Dan's final drawing, and yes, sometimes it actually turns into a real airplane. Then there are other considerations, which, I'm not going to get into a lot, but, you have to operate this in the ground. And this one, a friend of mine used to run an FBO and said, okay, you designers, you try to make everything lighter. Why, on God's earth, do you put the lav holding tank clean out port on the bottom of the airplane where some poor rampy has got to climb underneath the airplane in PPE and unplug that to drain the tank? Because if it doesn't unplug really cleanly, they need that PPE. So, but there's those kinds of considerations. For example, I know of one airplane where the ground start APU plug-in is on the same side as the engine you start first, which saves a few inches of wiring. It'd be a lot safer to have it on the other side, so you plug in on the right side and start the left engine, just for example. Ease of loading, all kinds of things like that come in. So with that, thank you very much for your attention, and we'll take questions if we have any time left. Yes. Well, on the tailless airplane, the aft limit is set by where the aerodynamic center of the basic planform is. There's nothing I can do to adjust that. The forward limit is set basically by the control power of the elevons. And so tailless airplanes, it's harder because you don't have the variability of the horizontal tail, and so your limits are tighter. And in fact, that's one of the reasons the conventional wing body tail has lasted so long, is because you have that degree of configuration flexibility to do something like I just showed you with the scissor plot. Anyone else? Well, let's see. Anyone else got a first question before we give this gentleman a second one? Yes, sir.
So a lot of home builders go back and forth over what engine and what horsepower.
Yep.
In an existing design, changing horsepower, what does that affect? You kind of covered it a little bit.
Okay. A lot of home builders, just to point out the question, home builders worry about maybe changing engines. The basic point is you have to look at the whole system level effect of changing the engine. You're changing the weight, you're changing the fuel burn mostly. So changing the weight means you have a CG implication, you have a structural implication on the engine mount, and if it's going to more power, because I have yet to meet someone who said, I'm going to put a lower powered engine in my airplane, you're probably burning more fuel. So now what does that do to your range and so forth? I'm actually watching a kind of a sad story happen in my neighborhood, because there's someone who built a relatively well-known kit airplane, but has chosen to mount a non-standard engine, and it's just discovered that in order for it to balance, he needs 50 pounds of ballast in the tail cone. Not going to happen. And, it's hard to tell him, you've got yourself in a corner, and none of us can help engineer our way out. Yes, sir.
So you mentioned that a lot of times early career engineers are right on the industry.
Yeah.
Only work on one or two aircraft in a career.
Yeah.
Which is possible, right?
Oh, it's possible. I know people who've done their entire career on the F-18, for example.
Yeah. So how do you decide when it's when something's mature enough that you want to move on to the next one?
Well, that's a very tough question. Because it's a challenge between career advancement, interest, job security. You know, if I've got a job maintaining a force structure airplane that's still in production, pretty good odds the paycheck's going to keep coming. But you could get pretty bored. You want to go out into a startup or a new project, you know, one of the things you learn if you're in advanced design is sometimes you win and sometimes you lose. And when you lose, everything stops tomorrow. You know, the best I can say is it's a winding road. I made decisions along the way because of what felt good at the time, and I got lucky. You know, but it's a balance, and everybody's, you know, and once again, this is a very personal thing, because everybody's got a different financial need, a different risk tolerance. I left a secure corporate job to go work for a startup for a while. That startup lasted 4 years and then went out of business. It was still one of the best decisions I ever made, because I met a lot of good people and I got around a bad roadblock in my career. I ended up going back to the same corporation, but in a much better position. How are we on time? Was the next speaker 10 minutes to go? Okay, please flag me when I get close to stepping on the other speaker. Okay, anyone else with questions? Murray.
Going back to survivability.
Yeah.
Chart, I got a chance to go to Tremendous NXT.
Yeah.
And it has a placard inside.
Yeah.
That says never under 140 knots.
Okay, so Murray's telling me about a race plane that has a placard that's never under 140 knots. Okay, this is a special mission airplane. Its only mission was to win races. So what this means is that the user of that airplane is accepting a risk that he will always have to be able to get to a smooth runway to put that thing down, or be high enough to bail out if he's got a parachute. You know? Necessary for the mission. If you just think speed is cool, maybe you don't take that much risk. Depends on the design, depends on the mission. Yes, sir.
So on your big lift that you have there,
Yeah.
if it's the true big lift, are those wing fences that are poking out of the leading edge? Is that
They're actually Vortelons, but yes, I was already worried about the stall on the Delta wing. You see, one of the things that goes to, and this is what comes with experience, is if you've worked on a lot of different airplanes and a lot of different configurations, you've got a pretty good idea of what kinds of problems you're liable to find, and you therefore start designing in advance the possibility of, if this happens, as is classically the case with a shape like that, how would I mitigate it? So, yeah. You know, and that one didn't survive the initial notional stage because it didn't balance. Yes, sir. Yes?
How does the material selection of carbon fiber affect your planning versus aluminum?
Okay, it's a very good question. What you want to do is take a look at the material and say, what loads do I have to carry? How hard is it to make? And how much will it weigh? So there are certain places in a structure where carbon fiber can make it a lot lighter. There it's worth doing. There are other places in a structure where what actually sizes the structure is either stiffness or ruggedness, and carbon fiber is actually a poor choice, so you can use aluminum. And once again, carbon fiber is more expensive than aluminum. So if I care about cost more than the last tiny little bit of performance, I'll probably go metal. If I'm trying to get that last little bit of weight, that last little bit of performance, maybe I go carbon or other advanced composites. But it's one of those fundamental choices. The other thing about carbon fiber and composites is you can build shapes in composite that are very hard to do in metal. So if I want to make a very curvy, flowing shape, I'll probably do that in either fiberglass or carbon fiber rather than in metal, because forming metal like that is a high art that I don't know how to do. All right, anyone else? Yes, sir.
Tell us about the startup.
Can I tell them about the startup? Yeah, it was a small company that was basically doing research and also had an in-house magic configuration. And one of the lessons learned there was that even a quantifiable, provable benefit has to be really large for a big company doing certified airplanes to be willing to take the risk of deviating from conventionally. And although our technology was real and it worked, it wasn't enough revolutionary enough. So that was the one lesson from there. And then, it was very interesting to get to do a lot of little projects and learn a lot. So, more risk, but more reward. All right, I think we have time for one more question, then I probably got to yield the stage for another speaker. Has anybody else got a first question before I give that gentleman his second? Yes, sir. Yes. I don't know. Well, did it have a CG problem? One of the problems with canard airplanes in general is if you're using the wings for the fuel tanks, you tend to get a big CG travel. That's why there are strakes on the Easies, and I think that's why Chet Nelson put strakes on the Sonic Cruiser also. But even though I knew the guy who actually did the design, it was all very proprietary, so I never got into the nitty-gritty enough to be able to tell. Okay, folks, I'm going to yield the stage now because the next speaker needs to be able to get in. Give me a couple of moments to collect my stuff, and then if anybody wants to talk, I'll be hanging out there to take it from there. Let me just press stop on